Dear colleagues, today I will present you my software, GeoSpring 1.0. So, this software was developed for the design of shallow and deep foundations, as you see. The development of such a product, it has started since 2015. So today we will see the futures of GeoSpring in the design of shallow and deep foundations. So let's go ahead. Basically, GeoSpring, it contains 4 modules. The first module, it's about the design of shallow and deep foundations. So it computes the bearing capacity and settlement. The second module, it's about pile foundations. So it computes the settlement of pilot foundations, single piles and group of piles also. The third module, it's about the design of rigid inclusions. And the final module, it's about the settlement of embankments. So the short-term and long-term settlement of embankments. So we'll see now how we pre-design a rigid inclusion alternative using GeoSpring. Actually, engineers, when they start to design soil improvement alternatives, they are looking for the so-called improvement area ratio, the percentage of substitution or replacement of the good material in the loaded surface. Okay, so we put a rigid inclusion. So here we put the layer type, okay, or the type of layer in the geotechnical cap, and here we put the thickness of each layer. Example here, let us say that it will be clay 5 meters, clay also 7 meters. After that it becomes sand, and sand here it will be 5, for example. Here it will be 5. Here you will put the deformation modulus and the Poisson ratio of each layer. For example, here it will be 7 MPa and 0.4. Here it will be 10 MPa and 0.4 also. For the sandy layers it will be 25, for example, and 30, 0.33 and 0.3, for example. Okay. Here you just have to put the width and length of your foundation. Okay. Let us say 3 by 3. The applied stress, for example, you will have 180 kPa. Okay. The embedment of your footing, for example, 1 meter. The water table at 2 meters. Here you have to put the diameter of your inclusion. Okay, for example, 0.6. The length of your inclusion, it will be here, for example, 5 plus 7, it will be 12, because at sand deformation moduli start to increase. They start to be stiff enough to not have a large settlement. So let us say 12, the length of the columns. The inclusion modulus, let us say, for example, 35 MPa, and the target settlement, for example, you would like that your target settlement will be 0.025, 2.5 centimeter of settlement. And here you push the button. You will have here the curve giving you the variation of the improvement area ratio as a function of the target settlement. For example, our target settlement was 2.5 centimeter target settlement. So you have to put 33.6% of your material, your rigid inclusion material, to attain this target settlement. To have 2.5 centimeter of settlement, you should put an improvement area ratio equal to 33%. But here you have all the curve with all the target settlement. For example, to know the improvement area ratio for 2 centimeters, you just project the value of 2 centimeter and you will have 45%. So actually this curve, it will be useful for you to know the improvement area ratio before starting your finite element or finite difference modeling to study the behavior of these columns in short and long terms. So this is like a kind of design chart allowing you to know about the value of the improvement area ratio, to not start like arbitrary numerical modeling without having target an appropriate value and waste your time in numerical modeling. Thank you very much and see you soon.